Thank you, Antonio, for the introduction. That's my first time with this EPIC format, and I'm quite happy about it that I'm allowed to join this. So I'm Claudia. I'm the CEO and founder of RobustAO, and today I would like to introduce a new dimension in laser cutting called dynamic beam shaping for high-speed, high-quality stainless steel laser cutting. I would like to start with a few words about the company. Well, the name of the company is RobustAO, and it means we do robust adaptive optics. So we are really a pioneer in the industrialization of high power adaptive optics. So to narrow it down, we do deformable mirrors for high power applications. We have a small team now, 8 people, but we are very experienced in the fields of designing deformable mirrors and controlling them very fast, and also in the application development. And last but not least, the company RobustAO is a spin-off of Fraunhofer here in Jena. The motivation for all this dynamic beam shaping is shown here in this picture. Normally in laser cutting, the cutting speed is mostly driven by the power or the brightness of the laser source. So the more power you have, the faster you can cut. And we were curious about dynamic beam shaping so that we can add another dimension to improve the cutting process, and we mainly focus on the cut quality without losing the processing speed. And the tool that we developed is dynamic axial beam shaping. So this means, I show you the concept here. We have a laser focus, as you all know, and we focus and refocus the light very quickly along the oscillation or along the thickness of the material and the propagation of the beam. And in general, we have 3 parameters. We have the oscillation amplitude, we have the oscillation frequency, and we have the oscillation offset. And the next picture shows you how the oscillation amplitude can shape the beam. So the oscillation amplitude in the end controls the width and the intensity distribution. So if you compare what is feasible, a static beam and a dynamic beam shaping beam, axial one, then you can broaden the spot diameter up to 250%, and you can increase or stretch the Rayleigh length by a factor of 12. And if you do this, like it's shown in this picture, you can see that the intensity, the energy, does not drop down too much on the rim, but is very constant on the very long shape. And this is really the trick of dynamic axial beam shaping. And the other degrees of freedom is the overlap. And I show you here two possibilities. So the overlap is tailored by the feed rate and by the oscillation frequency. And if you have a very low overlap, like minus 250%, then you can see that the beam is traveling like in a zigzag way. And if you have an overlap of 50% and above, then you have a constant energy distribution along the feed direction. So to sum it up, what do we do? RobustAO, we develop hardware that rethinks adaptive optics technology. And the product that we're doing is the Zwobble technology. Zwobble because we wobble in the Z direction, and it's a deformable mirror. It has a very thin mirror membrane here in yellow, and we have a piezoelectric actuator that acts on that membrane. And we have a sensor, because if you use piezoelectrics, it's quite fast, but you also have hysteresis and nonlinearities. And we want to have an absolute position feedback. That's why we're using the sensor. It is implemented in a standard cutting head as a 90-degree deflection, and it produces almost ideal biconic mirror deformation at the highest speed. To give you some numbers, The maximum oscillation frequency that we have now is 3,500 Hertz. And the minimal step response between minima and maxima deflection is below 2 milliseconds. So we are quite fast. This is our first USP, and the second one is that we like to work with high power lasers. So our actual limit is 20 kilowatt. That's because we were not able to test it with higher laser loads. And what we already showed up to now is that we have loads of quality improvements regarding edge roughness and loss. We have larger process windows, like higher nozzle distances, and of course we have higher cutting speeds. But now I go a little bit more into detail, and I would like to start with one of our latest results in the terms of fusion cutting of stainless steel. And we have here the results of the cutting speed over the laser power, and we compare our technique with the static focus that you probably all know. And you can see that the actual DBS is on all power levels faster than the quality cut of static focus. And in the low power of 8 kilowatt, we are more than 80% faster. And in the high power of 20 kilowatt, we are 37% faster, which is equivalent to 5 kilowatt laser power. And on the right-hand side, you see some details on the quality. So what we can see with the static focus, that the quality remains more or less constant with an average burr of like 200 micrometer. And with our technology, we can improve the burr at least by a factor of 2. And the most impressive results are with the maximum power of 20 kilowatt. So we achieved the highest speed and the best quality at 20 kilowatt. And here's the one-by-one result. In the upper picture, you see the static focus, which already has a really nice quality and low burr. And here on the lower side, you see our results with a better quality in times of burr, which is really, really little absent nano burr, how you would ever call it, at the high speed that is known for the separation cuts. And if you go a little bit more into detail, beside the dross reduction and the faster cutting, we also have a significant reduction of the roughness by, let's put it like by a factor of 2. So these results were all in the same sweet spot, so we don't have a difference between separation and quality cut. It's all the same in our case. This is another example in stainless steel, also a thickness of 10 millimeter, but with lower power. And this was a bevel cut. And you see also that we could reduce the burr to very, very little values, and we could also reduce the roughness of the cut. And the last example that I bring, again stainless steel, but a thinner stainless steel of just 5 millimeter. And we compare ourselves again to a very nice result with a static spot and also with very, very little burr. And we could have, with our technology, we could more than double the speed and keep the nice quality. And what we also experienced is that the process is more tolerant to nozzle distance changes. So it's a more robust process if you compare to a static spot. And finally, I would like to show you some results for the systems integration. So we made the integration into robot arms. If you have just low power, which is accessible by robot arms, if you have the beam inside the robot, it's available in a laser form machine for fine cutting. And it has also been tested in a Nukon machine for 6-sheet cutting up to 20 kilowatt. So to sum it up, we focus on quality improvements without losing speed. We provide quality cuts at separation cut speed. We show that we can really reduce nano burr in stainless steel. So our goal is always to remove any post-processing, but that you can take the part out of the machine and use it. And our current upper limit in laser power is 20 kilowatts. So if you have any 30 kilowatt laser and above, we would be happy to test it. And what can we do for you? So if you have any issues in cut quality in metal or also glass, independent of the wavelengths of your machining laser, please let us know. Any need in super fast light focusing, and we would also be interested to spread our experiments a little bit more into welding applications. So what can you do for us is if you have any issues in quality or would like to test the technology, then please let us know and we would be happy to help you. Yeah, so thank you very much and I'm open for questions.